25.6 Electric Dipole in an Electric Field. In this lecture, we will outline several key concepts. First, we will cover the definition of the electric dipole moment. Next, we will examine the torque exerted on a dipole when placed in a uniform external electric field. Following that, we will discuss the potential energy associated with a dipole and field system. We will also distinguish between polar and nonpolar molecules. Finally, we will look at a practical example involving the water molecule. Let us briefly recap the relationship between energy and dielectrics. When a dielectric material is inserted into a capacitor while keeping the charge constant, the stored energy changes. The initial energy is equal to the charge squared divided by twice the initial capacitance. The final energy becomes the charge squared divided by twice the product of the dielectric constant and the initial capacitance, which is mathematically equivalent to the initial energy divided by the dielectric constant. Because the dielectric constant is strictly greater than 1, the final stored energy is less than the initial energy. This decrease in energy is accounted for by the negative work performed by an external agent, which is necessary to keep the dielectric from accelerating as it is pulled between the plates. A practical application of this capacitance change is a carpenter's stud finder, which uses a capacitor with side-by-side plates rather than facing plates. When you move the device over a wall, the material between the plates changes from a combination of wallboard and air to wallboard and a wood stud. Since wood has a substantially higher dielectric constant than air, this physical change increases the capacitance of the device. The increase in the dielectric constant triggers an internal circuit, causing a signal light to illuminate and helping you locate the hidden stud. Now let us define the electric dipole formally. An electric dipole consists of two charges of equal magnitude but opposite sign, separated by a specific distance we call 2a. The electric dipole moment is a vector quantity that is directed from the negative charge toward the positive charge. Its magnitude is defined simply as the product of the separation distance 2a and the charge q. This vector moment helps us quantify the separation of charge within the system and will be used to determine how the dipole interacts with external fields. Imagine placing this dipole in a uniform external electric field at a certain angle. The net force acting on the entire dipole is identically zero because the electric forces on the two individual charges are equal in magnitude but perfectly opposite in direction. However, because these forces act at different locations, they produce a net torque about the center of the dipole. The magnitude of this torque is the product of the dipole moment, the electric field, and the sign of the angle between them. In formal vector notation, the torque is the cross product of the dipole moment vector and the electric field vector. This resultant torque tends to rotate the dipole to align its moment with the external field. When an external agent does work to rotate the dipole against these forces, that work is stored as electric potential energy in the system. The change in potential energy when the dipole rotates from an initial angle to a final angle is found by integrating the torque over that angular displacement. If we conveniently choose our reference point of zero potential energy at an angle of 90 degrees, the potential energy at any given angle is the negative product of the dipole moment, the electric field, and the cosine of the angle. Using standard vector notation, this potential energy is simply the negative dot product of the dipole moment vector and the electric field vector. It is very helpful to compare this electric behavior to gravitational potential energy, which we studied previously. In the gravitational case, the entity parameter is mass, while for the dipole, it is the dipole moment. The field parameter is the gravitational field for a falling object, compared to the electric field for our charge system. The configuration depends on vertical position in gravity, whereas it depends on rotational position or angle for the electric dipole. In both systems, there is a natural tendency to return to the original configuration of lower potential energy, such as a mass falling toward the ground or a dipole rotating to align itself with the field. Next, we examine polar molecules, which are molecules possessing a permanent separation between their positive and negative charge centers. The common water molecule is a prime example because of its nonlinear geometry, specifically exhibiting a bond angle of 105 degrees. This geometry results in the oxygen end being negatively charged and the hydrogen end being positively charged. A highly practical household application of this property is soaps. Soap surfactants contain a polar end that readily attaches to water and a nonpolar end that attaches to grease, allowing plain water to effectively wash away oily dirt. In stark contrast to polar molecules, perfectly symmetric molecules do not possess any permanent polarization. However, when such nonpolar molecules are placed in an external electric field, the field shifts the charge distributions within the molecule, creating an induced polarization. The center of negative charge moves slightly relative to the positive charges. This induced polarization effect is the primary mechanism for how dielectrics function when they are placed inside capacitors. Let us consider a numerical example where we calculate the work required to rotate 10 to the power of 21 water molecules. We start with all the dipole moments completely aligned with the electric field at an angle of 0 degrees, and we rotate them to an angle of 90 degrees. The initial energy of the system is the negative product of the number of molecules, the dipole moment, and the electric field magnitude. The final energy at 90 degrees evaluates exactly to 0. Therefore, the total work required equals the difference, which evaluates to the positive product of the number of molecules, the dipole moment, and the electric field. Plugging in the given numerical values yields a total required work of 1.6 times 10 to the negative 3 joules. Looking more closely at the atomic description of dielectrics, we see that an external electric field polarizes the material. This overall polarization occurs by partially aligning polar molecules or by distorting the charge clouds of nonpolar ones. This physical process creates an induced surface charge density on the outer faces of the dielectric slab. These newly induced charges then generate an internal electric field that points in the exact opposite direction of the original external field. Consequently, the net electric field magnitude within the dielectric is the original external field minus the induced field, which is exactly equal to the external field divided by the dielectric constant. To summarize our discussion, the electric dipole moment has a magnitude of 2a times q and is directed linearly from the negative charge to the positive charge. External electric fields exert a predictable torque that tends to physically align the dipole moment with the field direction. The potential energy of the entire dipole system is minimized when the dipole moment is perfectly aligned with the external electric field. Finally, dielectrics alter capacitor behavior by reducing the internal electric field through the mechanism of molecular polarization, which can be either a permanent characteristic or an induced effect. Before we conclude, please consider these review questions to test your comprehension. First, why does the net translational force on an electric dipole in a uniform electric field strictly equal 0, while the net rotational torque does not? Second, thinking carefully in terms of work and energy, why is the specific configuration where the dipole moment is perfectly anti-parallel to the electric field considered a state of maximum potential energy? Take some time to review your class notes and formulate answers to these questions to solidify your understanding of electric dipoles.